So as we have seen in laminar fluid flow that the adjacent layers of the liquid are parallel to each other, there is no intermixed adjacent layers of the liquid. So during this flow we have evaluated what is equation of shear stress, as well as we have seen what is equation of velocity. Along with that, we have studied what is average velocity and the head loss through the pipe. So let us apply all these formulas to solve a real life problem on laminar flow. Okay, so let us consider a problem which is related to laminar flow, which states that a crude oil of viscosity 1.5 poise have a relative density 0.9 flows through a 20 mm diameter vertical pipe. Very important, that is given to you as it is a vertical pipe. So there is a crude oil which is traveling in a vertical pipe, which we don't know whether it is going from the bottom to the top or from the top to the bottom. So what else is given? The pressure gauges are fixed 20 meters apart. So in that the pressure gauges are kept 20 meters apart. So we know what is the length of the vertical pipe, which reads 600 kilonewton per meters at the lower side and 20 kilonewton per meter at the upper side of the pipe. So we know what is pressure at the higher end and at the lower end. We have to find the direction of the flow and the rate of flow through a pipe. So how much is the amount of flow through the pipe and direction of the flow. So let us draw this diagram for this entire part, as well as we'll write down all the data which we know in this problem. So let us write down the things which we know. That is, first, data. First, they have given us what is a viscosity, that is 1.5 poise, which is equals to 0.15 Pascal seconds. Next, what is given to you? That is a relative density, that is a density of oil to density of water, which is given to you as 0.9. So 0.9. So that becomes, density of oil becomes 900 kg per meter cube. So that is what given to you. Next, what they have given to you is the diameter in the vertical pipe. So diameter is equals to D is equals to 20 mm. Next, reads pressure at the inlet and pressure at the outlet of the pipe. The pressure at the inlet and the outlet. So let us consider the lower side at the inlet and the upper side as the outlet, which we actually don't know till the time we don't calculate the direction. So let us assume that the lower side is the inlet and the upper side is the outlet. So that is given to you as 620 kilonewton per meter square. So let us write down, this is 600 kilonewton per meter square. This is 20 kilonewton per meter square. Length of the pipe, which is given to you as 20 meters. So we have to calculate the flow rate of the pipe. Now here they have not specified whether the pipe has a converging diameter or a diverging diameter. Rather, it is converging or diverging. We'll assume that the pipe diameter is constant. So now let us draw the diagram of the pipe. So there is a vertical pipe. Now, this vertical pipe has two sections. This is section 2, we'll assume. This is section 1, and during this, we know that it is 20 meters apart. This is 20 meters apart. Pressure in section 1, which is given to you as 600 kilopascal or kPa, kilonewton per meter square. Pressure in section 2 is 20 kilonewton per meter square. So we don't know the flow of the fluid. So now let us calculate this. For this, we have to apply what is Bernoulli's equation at section 1.1 and section 2.2. So, if the total energy at section 1.1 is greater than the total energy at section 2.2, that means the fluid is having a higher energy at 1 and a lower energy at 2. So, the fluid won't flow from a lower energy level to a higher energy level. It will always flow from a higher energy level to a lower energy level. So now let us apply Bernoulli's equation for this vertical pipe. So our Bernoulli's equation states that is the total energy at section 1.1 will be equals to P1 upon rho g plus V1 square by 2g plus Z1. This is what is the velocity. This is what is the total energy. So, and total energy at section 2.2 will be P2 by rho g plus V2 square by 2g plus Z2. Now, over here, one of the most important thing which we know, that the pipe diameter is not changing. Since the pipe diameter is not changing, the cross sectional area is constant. If the cross sectional area is constant, we can write that V1 is equals to V2. Both the velocity across the sections are same because area of cross section is same. So now we'll evaluate the value as total energy at point 1. So this is equals to 600 into 10 to power 3 upon 900 into 9.81 plus V1 square by 2g plus Z1. Now we'll consider this part as 0. We'll consider this as the datum line. So this is the datum line or the reference line. Hence Z1 is equals to 0. When we come to section 2 to Z2 will be equals to 20 meters. So let us evaluate this value. So calculating this entire part will give us the value as equals to, that is 67.97 plus V1 square by 2g, that is equation number 1, that is total energy at section 1.1. So we have evaluated the total energy. Let us evaluate what is total energy at section 2.2. So section 2.2, the pressure over here is 20 into 10 to power 3 upon 900 into 9.81 plus V2 square by 2g plus Z2. Value of Z2 over here given to you as 20 meters because the section 2.2 lies at a distance of 20 mm from section 1.1, which is at a higher level. So now let us substitute the value. Evaluating this will give you a value of 45.65 plus V2 square by 2g. Now, just now we proved one thing, that the velocity V1 and velocity V2 both will be same. Why both the velocities are same? Because they have a uniform cross sectional area. So you can see that the total energy at section 1.1 is greater than the total energy at section 2.2. So let us write down this part, that is total energy at section 1.1 is greater than the total energy at section 2.2. Now what does this imply? That the lower level, that is the lower inlet, has a higher energy and the upper inlet has a lower energy. So during which this will flow from section 1.1 to section 2.2. This is the direction of flow. This is the direction of flow. The next thing we have to calculate is what is the flow rate in the pipe. For that, we need to know what is the head loss. So the head loss due to friction is given as 32 mu mu u bar L upon rho g d square. Now, this is the head loss due to friction. This is the total head loss during that entire flow of pipe from section 1-1 to section 2-2. So now let us evaluate this. During this evaluation, we know the value of viscosity, which we know. We know the value of length of the pipe, diameter, rho and g, all are known except the value of u bar. So that can be evaluated by the difference in the that can be evaluated by calculating the difference in the head. So let us evaluate this. So the head loss due to friction is 32 into mu is 0.15, u bar length is 20 meters upon 900 is the density, 9.81 is acceleration due to gravity, and the diameter which was given to you as equals to 20 mm. So this is 0.02 meters, that is 20 into 10 to power minus 3. So now let us evaluate this. Is 0.02 square, so which comes out to be 27.183 u bar, that is head loss due to friction in that entire pipe. Now, this head loss due to friction in the entire pipe is equals to the difference in the head loss at section 1-1 and section 2-2. So now we know the formula of piezometric head. Piezometric head, that is HF, that will be given as a loss of piezometric head, which is equals to P1 upon rho g plus Z1 minus P2 by rho g plus Z2. Now here in piezometric head, since the velocity is not changing between section 1-1 and section 2-2, we will not include V1 square and V2 square. Technically speaking, in this formula, there should be V1 square as well as V2 square. That is called as what? Piezometric head. But we won't take into existence because both the values of V1 and V2 is same, having the uniform cross-sectional area. So now let us substitute the value. On this part comes out to be 60 into 10 to power 3 upon 900 into 9.81 plus 0 minus of 20 into 10 to power 3 upon 900 into 9.81 minus 20. So this comes out to be 25.3 meters. So that is the head loss due to piezometric head. Now, the head loss due to piezometric head, let us consider this as equation number 2, and the head loss due to the friction between section 1-1 and section 2-2, let us consider this as equation number 1. Now we can see that both the head loss are head loss in the pipe between section 1-1 and section 2-2. So now let us equate this head loss from equation number 1 and equation number 2. So what do we get over here is 27.183 u bar is equals to 25.3. So u bar will have a value of 0.9307 meters per second. So we have evaluated what is value of u bar, that is the average velocity between section 1-1 and section 2-2 in a horizontal uniform diameter pipe. Now let us calculate what is the flow rate in this vertical pipe. So the flow rate will be given as Q into area of cross section into U bar, that is equals to pi by 4 into D square into U bar. So this is pi by 4 into 0.02 square into 0.9307, which comes out to be 2.94 into 10 to power minus 4 meter cube per second. So that is the flow rate in that entire pipe. So now we have calculated the direction of the pipe, direction of the flow, not the pipe, and we have calculated the flow rate. So I hope you have understood how to calculate the rate of flow as well as the direction of the flow for a uniform diameter vertical pipe using the concept of laminar flow. Thank you.